So thanks for coming to my talk. This is about Graviola. It's a new cryptography crate for Rust. You may know me as the original author of Rustles or Rust TLS, call it either name, I don't mind. I've actually looked back, and the first Rust code I ever wrote, which I almost immediately discarded in October 2015, so a few months after 1.0. So I think I was in that first wave of people going, oh, 1.0, that probably means it's good. So what I'm talking about today, almost like half of this talk is trying to give you an intuition about what I want from cryptography code, about side channels, and why maybe it's not such a good idea to write lots of cryptography code which is side channel sensitive in high-level languages with optimizing compilers. Then I'm going to talk about a bit more about this project, starting with this project out of AWS called S2M and how I'm consuming that in Rust. And then we'll talk about the actual project itself at the end. So what do we, and I say we, this is not like a generally accepted thing, this is just like an opinion of one person. So I wrote this sort of Maslow's hierarchy of needs for crypto code. And the first thing we want is to produce the correct answer. Hopefully that goes without saying. The second thing kind of builds on that, and we always want to produce the correct answer. So it's like the first one, but reliably. And I'll talk about that in a second. And then without leaking secrets, so this is all about side channels, and then quickly. So you can get to the first one just by basic testing gets you most of this. So that's kind of boring. The next one is really exciting and quite current, to do with formal verification. So there's this example, which is a very instructive example in Go's P256 implementation, where there was just a very, very subtle bug, and it only happened 1 in 2 to the 32 times. So there were the same class of bug. You can have even worse error rates, 1 to 2 to 64, which is almost impossible to find randomly. So no amount of differential fuzzing or anything will find you these bugs. You're not going to be able to do 2 to 64 times some constant number of tests. It's just insane. But we have this thing, formal verification, which proves that the code is bug-free in this respect. So that's good. And this is a particular problem in crypto code, where if you make this sort of error, it's very, very common that it's massively exploitable. And there's this really good talk, I think, that you can find that on YouTube, about how that can actually happen in practice. And then the next thing I said is about side channel safety. I'm going to talk about that in a minute. And then performance. Performance is kind of boring in a sense, because it's a well understood problem. You measure the thing, you work out how to make it quicker, you make it quicker, you measure the thing over and over again forever. There's lots of literature. Intel and ARM produce reference implementations and white papers telling you how to make things quick on their CPU. You read those, you go, well, that sounds like a good idea to start with. And yeah, so I'm not going to really talk a lot about performance until really the end, when I present some benchmarks. About side channels. So let's think about a cryptography function. And it's going to be a pure function, so it doesn't have any state. Any state either has to come as an input or be emitted as an output. And then we're going to classify these inputs and outputs into secret and public. So public ones, you can go out on the street and you can shout, and nothing will happen, nothing bad will happen, but obviously the secrets have to stay secret for anything to be secure. So an example, if you're doing like a normal signature, say this is like a signing an email. So your message, you're going to send that over email, that's public. Signature, you're going to send that over email, that's public, but your private key is private. That's a sort of fundamental idea. But then in cryptography, we've also got things which don't involve any secrets, like verifying that signature. All the inputs and outputs are public. So this sort of function involves no side channels. There's just fundamentally no secrets to leak. And so the way you optimize this is very different to a function which involves secrets. And now I'm going to add a third thing. And that's called, you can think of I'm calling this a trace because that's kind of what the literature uses a lot. But you can think of this as like a log file of everything the CPU did during this function. And to be more concrete, it's made up of two parts, like an instruction trace, so every instruction that you executed during that function, and every memory access. So like the order of them, where they are, the address, all that stuff. And note that the register contents and the memory contents aren't in this thing because otherwise we couldn't keep any secrets at all because we'd just be, immediately exporting them. And the point of this trace is like this is not a literal thing. This is like a thought experiment. And we're going to give this trace to our attacker and say, like, this is all the information that you can possibly get. And we're going to ignore the fact that, there are ways for an attacker to get basically all this information, but at some reduced level of clarity. So there might be some noise, they might have to run the function a million times, but we're just going to ignore that. We're going to give them a perfect 100% view of the world. So it makes our adversary as strong as possible. And now we're going to set ourselves two goals. And the first goal is that no secret input has any dependency on the contents of that trace. And what's the sort of counter to that? If we don't meet this, like we have a branch on a secret, then we end up with a whole load of possible side channels. And if we have a memory, a secret dependency on the memory trace, then we usually have like a cache side channel or some other timing side channel. Unfortunately, that's not enough because some instructions take a different amount of time, a different number of cycles, depending on their value. Division is a common example. Multiplication on some CPUs is another example. So we're just going to ignore those instructions and make sure they don't exist at all in our trace. So we haven't, divided using any secret data. On ARM, there's a relatively new thing called data-independent timing, the DIT bit. And you have to set this before you do any cryptography because at some point in the future, I guess Apple will release a new ARM CPU which takes advantage of this. By taking advantage of this, I mean they'll make addition of 0 very quick. Multiplication by 1, that'll be very, very quick because it's trivial. But that's the kind of property we don't want in our cryptography code because it would, ruin the whole game. There's an example there as well of a quite recent vulnerability where cryptography code used division, and that didn't go well. This was actually in the reference implementation of a new post-quantum algorithm. So it's, again, very new code. This isn't like stuff that was knocking around since 1997, written in the last couple of years and didn't meet this goal. Now I'm going to talk about optimizing compilers. No pitchforks. So they're bad for cryptography, and I'm going to say why. And this is not specific to Rust. This is pretty much every optimizing compiler which is fast, produces fast code. And the reason is we basically can't tell the optimizer about those goals. We can't say, this is secret, so you must not branch on it, for example. And what people writing cryptography code do is they know this, they know those two goals, they share those two goals, so they try and write the code in a very sort of Baroque, weird way, where the optimizer can't really work out maybe that, you know, it can't work out that it can put a branch there, but eventually that doesn't go well in a future slide. So we did have a design to improve this. This came out of a workshop I was at called High Assurance Cryptography in Software in 2020. And I think it was a good idea. I think it's still a good idea. But unfortunately, it didn't go anywhere. And I think the reason it didn't go anywhere is fundamentally it required work on the Rust compiler side and work on the LLVM side. And from the point of view of the LLVM people, they were like, well, there's no one going to use this, so we're not going to do this work. On the Rust side, it was like, well, LLVM doesn't support this, so we can't produce something useful. So this is like impasse where fundamentally both have to agree that this is a good thing to do and do it in concert. And that kind of didn't happen. But it did, that RFC, that one, look it up. It's got a really good and long discussion from lots of really good people about side channels, about Rust, about cryptography. And there's this quote from Peter Schwabe, who is a really well-known cryptographer. He's responsible for a lot of, especially post-quantum algorithms that are being standardized now or standardized the other year. But basically, well, you can read it. This is sort of my justification for this whole section of the talk. And this hope for the best thing, well, how is that going? Not very well. So these things are both fixed and fixable, but they're fixable in a kind of doesn't really fix the real issue sort of way. Because again, we don't have a way to tell the optimizer that fundamentally you shouldn't be, you can't understand what we want from this code. So now on to the assembly part. So in this project, I'm really heavily relying on this project, S2M Bignum, which is a load of formally verified cryptography assembler routines. And formally verified means, well, kind of going back to my hierarchy of needs, is making sure there's no like carry bugs, making sure the arithmetic is actually kind of correct. And by kind of correct, I'm underselling it because it's like formally correct. There are 0 bugs in this bit of code. Exactly, you know, a function which adds two numbers adds two numbers. It doesn't like add two numbers, but every so often it will add like a huge multiple of them or something. And so that's really powerful because it gives some confidence to using assembly, because you know that there's a class of bugs, not all classes of bugs, but a class of bugs that does not exist in that code. And in their README, they've got quite a kind of detailed argument about side channel safety as well. I would say side channel safety is not one of the things that's formally verified. The thing that's formally verified is like mathematical equivalence to addition, multiplication, and whatever the function is implementing. So now talking about entering the sort of Rust section of the talk, you have this like traditional thing where you can get your assembly files and you can assemble them, and you can get object files, and then you link those all in. And I'm not going to spend a lot of time on this slide, but suffice to say, this is one of the things I was trying to avoid in this project, is having lots and lots of build time work and build time complexity on the kind of end user side. Because there are already crates with that, where you need a C compiler, you need an assembler. Instead, I'm doing this other thing, which you may think is a bad idea, which is to take this standalone assembly and massage it into inline assembly in Rust functions. And that gives some advantages, because you only need Rust C now to compile the whole thing. All this work is done at like a development time, so the outputs are just Rust files that you can check in. And Rust C can handle, it can do inlining, so it can like inline one of these functions into its caller, so that's a little bit of a performance improvement. And it handles all the ABI, which is different on different platforms. So to give you a sort of flavor of what this looks like, those assembler files use the CPU processor to do, renaming of registers, to have something readable. So here we're just like naming some variables, P and Z. And so we can convert that automatically into Rust macros. And that works pretty well. So you end up with lots of macros, but this is all private to the crate, so no one really needs to worry too much about that. And then you can have more complex macros, CPU processor macros, which end up like being convertible to Rust macros as well. And I think this works pretty well too. Like I said, since we're leaving all the ABI concerns to the Rust compiler, we can throw away all the ABI handling in the original code. And this bit of assembler is basically just reordering some registers to adhere to the weird, kind of pointlessly different Windows ABI. And then this slide is sort of a more generic overview of like an example. So one thing I'm trying to do here is maintain the readability, such as it is, of the input assembly, maintain all the comments and maintain all the naming, and basically make it so that if you look at this code, you can see it's the same as this one. And that's more of an aesthetic thing, but it was one of the goals here. This is not completely automatic, so you do need to write some stuff. You do need to tell this system what you want it to do and how to do it. And these highlighted bits, so you need to write a function declaration in Rust. So here we're adding two numbers and writing the output into a third. And then we also need to say how to input those parameters into registers so that the assembly can operate on them. Right. So about Graviola, it's a fruit. If you come across a Graviola, it's not very common in the UK, but I would suggest trying it. It tastes a little bit like banana, but it has the consistency of melon. Very interesting. You can also get it as a drink. It's also called soursop or guanabana. Anyway, that's not important. About the crate. So, like I said earlier, there are lots of cryptography crates, and they have varying amounts of like performance and build requirements. And I wanted this to fall on the easy and fast to build end of that spectrum. And obviously with my other projects, the whole goal is to make this work nicely with Russells and have decent performance. The other thing is about licensing. So at the moment, the common cryptography used with Russells all has a kind of lineage back to the original kind of 1.0 era OpenSSL. And so that has the OpenSSL old weird license, and some people really don't like that. To the extent that people come up to me at conferences last year before I started this project saying, please, I don't want to use the OpenSSL. Anything with the OpenSSL license, it causes me suffering. So where are we right now? I think it's easy and fast to build. So you only need Rusty. There's no build RS, there's no proc macros. A highly scientific measurement on my 2 development laptops, it compiles under a second. And it only has 2 dependencies, which I think are dependencies you probably already are consuming somewhere else anyway. And it's triple licensed under the same license as S2M Bignum and Russell's, so that's quite a common thing, I think. But at least it's a superset of the common Rust license of Apache 2 and MIT 0. And what features, so this is a kind of boring slide, but the point of it is this is the cryptography you need to talk to the vast majority of TLS servers on the web. And the other thing to say is like where this stuff has come from. So all the public key stuff is backed by S2M Bignum, and all the symmetric stuff is kind of new Rust code that heavily uses intrinsics to make it quick. And obviously there's some limitations, and using assembly with 2 architectures, that's a big limitation. Depending on who you are, maybe you only care about deploying something on AWS or like common phones or common laptops, in which case this is probably fine. But if you're in any way sort of embedded focus, this probably won't work for you. And the other limitation is I have a kind of goal to keep this to widely used cryptography, so it's kind of boring cryptography, if you like, nothing very, very bleeding edge, no weird zero knowledge proofs or anything. And yeah, you can use it. So there's actually 2 crates. There's a Graviola crate, which is like the thing with all the cryptography in. And then there's a second crate called Russell's Graviola, which obviously takes the dependency on Russell's and Graviola and joins them together. And then this code on the right is basically the way you interact with Russell's to tell it to use Graviola rather than something else. And there's a load of like cargo features you will have to mess around with on Russell's to stop it building all the other ones, but that's at least possible. And there's an example showing how that is done. So let's talk about performance. So I'm publishing, I wrote and am publishing benchmarks, including Go, because I have a lot of love for the Go, specifically the cryptography in the Go standard library. I think that's really good. And before I started this project, actually what I thought this project was going to be was literally just stealing all the cryptography out of the Go standard library, but I didn't do that in the end. Anyway, so what you're seeing here, this is a web page, and each row is a different operation on a different type of CPU. So again, it's my 2 laptops, which is like a Mac and a framework with an AMD processor. Each cell is sorted left to right from fastest to slowest. And then Graviola is highlighted green. So when I say competitive performance, the thing I've got in my mind is like top 3 in this table. And this is where we're at right now. So I think that's pretty good. I would say that some of this is like, this is not like performance at all costs. So P256 is really widely deployed, really widely used on the web. And you can make that quicker by having a huge table of stuff, like pre-computed values. And so Graviola has 150 kilobytes of such tables. And that's why it's quite quick here. P384 is not so widely used. And so I don't have such a big table for that because it's like it would be hundreds and hundreds of kilobytes, and I don't think the performance is that important. If suddenly the world changes and everyone starts using P384, the performance will go up, but at the trade-off of everything being a lot bigger. So yeah, there's space here. What else? Yeah, so how are we doing for time? Okay. What am I talking about here? Well, the main point here is I'm trying to keep all the unsafe code in a single place. So you can actually deny unsafe per module. So that's what I'm doing here. Basically, mod low is the only place you can have unsafe in this crate. And that means that when you're doing like parsing and stuff, there's absolutely no way that you can accidentally introduce an unsafe there. The compiler just won't allow it, which is nice. And here's like an example of what's in each bucket. I would say the two kind of top modules here are kind of artificial, but generally parsing goes in the top one, complex arithmetic goes in the middle one, and then a low-level arithmetic goes in the bottom, the lowest one. And this is roughly how big the crate is. And so you can see the massive amount of assembly here is not really that surprising, but I think Rusty's actually doing quite a good job to compile all that. I would say not all that, because only half of this is active at any time for each platform. So it's like 40,000 lines of code in less than a second, which is pretty good, I think. Other things, I'm a macro enjoyer. I like macros, and I will use them at any possible opportunity when I don't have a co-maintainer to tell me no. So this on the left is ASN1 syntax, and you might see this if you ever read a cryptography standard. They use this really weird thing from the 80s. You were meant to feed this text into a compiler, and it would generate you a load of code to like decode and encode these values. Practice, people don't really do that. It never was very fashionable to do that, I don't think. So people just handwrite this stuff and they go, oh, well, I expect a sequence, and I expect the sequence to contain 2 integers. So why don't we go back to the 80s and just like do it this way, where we can wrap the whole lot minus comments. So the -n, -e, we can't do that in Rust because you don't get line endings in macro rules macros. Maybe someone can convince me to use proc macros, but yeah, that's probably no. And then you get a structure containing those things, and you can decode and encode it, which is nice. And you can do that with object identifiers as well. And again, the whole point here is like, well, I think the whole point is to show off. But the other point is to make like the source code obviously the same as the standard you're implementing. So the other thing is, I mentioned the data independent timing bit. So every public function that's like an entry point into this crate starts with one of these lines basically designating it as a secret function, like, which is any function that has any secret inputs or outputs, or a public function, which is like the opposite. And the secret functions try and do, they turn on the dit bit and they turn it off on exit. They also try and do a bit of secret scrubbing. This is kind of work in progress. But eventually I'd like to scrub the whole stack, scrub all the general purpose registers and the vector registers. The vector registers actually works already. just to make it absolutely bulletproof and yeah. So yeah, what was the point of this talk? I think assembly is a good choice for cryptography. I wouldn't write general purpose code in it, but if someone's done the hard work of making really good quality assembly, it would be rude not to use it. And the performance is good. That's the other thing. The performance is really very excellent for a lot of S2N big num functions. And the other thing is, yes, you can kind of take stuff using the C preprocessor and use the Rust macro processor. It's not a preprocessor. Instead, maybe that's not like an incredible notion. I don't think that's a general rule. You can't do it for every possible C preprocessor usage, but certainly for the limited set in S2N big num you can. And yeah, for supported architecture, I think this is a pretty good new addition to cryptography for Rust. Yeah, that's it.
Any questions?
Thanks. Why did you build Graviola when there's already 4 other crypto libraries in Rust, I'd say?
That's a very good question. So I wasn't completely satisfied with any of them. There are ones which are fast but annoying to build. There are ones which are lovely to build but not very fast. Actually, to be honest, so that's like one kind of post justification, if you like. But the real justification is all my projects come from finding something that I can use that someone else has made and going, well, what if I take this and do something else? So actually, Russell's, I originally started that when I came across Brian Smith's Ring and WebPKI library, which was like 2 of the big parts that you need for a TLS library. And I was like, well, let's take those things and take them to a further conclusion. And this project is similar. It's like seeing S2N big num and like, well, what conclusion can I take from there? So like I say, it would seem rude not to use this stuff and kind of in an experimental way work out how it can be brought to the Rust ecosystem.
I know you showed the example of Graviola being introduced into Rust LS with the default provider. Is there any plans to make it permanently the default, and how will that affect the targets that Rust LS is being used on?
Probably not at this point. And I think this project is very young, so I only started it like last July. At the moment, the default in Russell's is AWS LCRS, which is really good. It has like a professional maintenance team who like actually work on it, are really good. And I think that's an excellent default. I should also say the performance is really good, like I showed in the thing. So that I think is probably the best default for Russell's. In general, what I'd kind of like to move away from is having more providers in the Russell's crate. I'd like there to be more providers outside. So to use Russell's, you have to like get this core crate, which doesn't have any cryptography, and pair it up with your choice of cryptography. We're not there yet. I think that would be quite annoying to many, many people. But certainly when there's a lot of choices with people demanding that choice, then that sort of architecture becomes a bit more tenable.
I know you mentioned that you saw this interesting library and you wanted to use it. Is that the only reason why you made Graviola and introduced it to Rusty Less?
There was certainly the license thing as well. That wasn't like one of the main goals, but it was certainly a goal that I was wanting to hit. And if, for example, if STM Big Num was all licensed under the OpenSSL original license, then I would probably have not done this project at all, because it's like, well, you just made another thing, which is like all the other things with the same rough performance, and why? So, yeah.
Yeah, it's a great talk and project. Thank you. So the question is about the formal verification. You mentioned it. So does it apply only to this Big Num library or to you as well?
Only to the Big Num library. Mm-hmm. So there is a varying, how do I explain this? The Big Num library operations range from very low level, like adding numbers, to very high level, like the entirety of the X25519 key exchange. So there's a uneven amount of unverified Rust code in play here. But yeah, I would say that none of the Rust code above the assembler is subject to any sort of formal verification. So yeah, the answer is different depending on the algorithm, which I see is not a very convincing answer.
And also, do you apply fuzzing or property-based testing and other stuff to test implementation in Rust? Just to verify that it works correctly.
Sorry, could you repeat that? I didn't quite get the start.
Sorry?
Could you repeat the question?
Yeah, sure. Do you apply fuzzing techniques or some kind of testing with different inputs just to verify that Graviola works correctly?
Yeah, so I do some differential fuzzing, which is you basically have a new thing and a thing that you kind of trust, and you just generate some random inputs, like structured inputs, like do a key exchange with these two keys, and then check that the result is the same. So that doesn't have a huge amount of like CPU power happening daily, but I'd like to add this to OSS fuzz to get some free CPU minutes on that.
I thank you for the talk and for the great project. I think I'm not making it up. In the beginning, you mentioned the PQC, and well, it's becoming known now that NIST is trying to phase out RSA. Do you have plans on adding like deprecation on the RSA and how PQC is supported?
Yeah, so that is definitely a plan. I haven't done anything for it yet. I think the STM Big Num people are working on kind of equivalent building blocks for things like ML-Chem. And so ML-Chem is the thing that I'm mostly interested from there, because I think it's well, this is just another opinion of mine. I think it's kind of premature to start thinking about post-quantum signatures and stuff. That doesn't really make sense. Not many people have requirements for very, very long-lived signatures, especially on the web. But for key exchange, it's definitely something I'm very interested in, and it's something that Russell's shipped support for last month. So, yeah.
Any more questions? Thank you, Joseph.
Thanks.